Okay, so let's go ahead and start up. Okay, so today's class, it's on signed binary numbers and also signed binary addition and signed binary subtraction by addition. And this information is important for the next lab 4. You'll only be able to do a small portion of lab 4 today. And then on Thursday, I'm going to talk a lot about lab 4. Today's going to mostly be lecture and some activities. Like I said, the lab portion is only a little bit you can do. But then Thursday's mostly lab 4. And if you look at the schedule, lab 4 is not going to be due until after the midterm. So the midterm is Thursday of next week. And then lab 4 is due the day after, like that Friday. So instead of being due Monday, like they have been, lab 4 is going to be Friday of next week. So you have more time to do it. You're going to see lab 4 has quite a few components. And also, what I have found, in the past, is that out of all the different labs this quarter, usually lab 4 is the one that, if people have some difficulty with, it tends to be this lab. And it's not so much that there are, more components. It's more just having an understanding of signed binary numbers, and specifically a format called 2's complement. Okay. So anyway, for those reasons, that's why, like I said, you got more time for lab 4. But like I said, today's going to mostly be lecture along with some activities. Now, also, I've had some people contact me that they're interested in changing lab partners. So if you want to change your lab partner, send me an email by tomorrow night. And then on Thursday, I'll announce what the new groups are. Okay. Sometimes people just want to change lab partners because they just want to meet other people. Other times they might know somebody in the class that they worked with in a different class, or they know from a different class, and they work better with that person. So, but whatever the reason, if you want to change lab partners, like I said, send me an email by tomorrow night. Now, if you don't want to change, if you want to just stay with the person that you're currently with, then don't send me an email. Okay. All right. So where we're going to start today is with something we've already talked about, you've already used, and that's unsigned binary numbers, right? Because prior to this class, we haven't talked about how you can use, binary to represent signed values, right? We've only taken them as unsigned. So somebody give me a binary number, just any number. What do you want me to start with? A 1, 0, 1, 1. Did you want to you wanted a 0 there? Or we'll go to 0? Okay, we'll go with 6. So as we talked about, when you have a binary number like this, that's unsigned, the furthest to the right bit that we call the least significant bit, that's the 1's column, right? So 2 to the 0. And then the next bit over is the 2's column, 2 to the 1. Then the 4 is 2 to the 2. 8, 2 to the 3, 6, 2 to the 0. The next column is 16, 2 to the 4, and 3 to 5, which is 32, right? Because remember, as you go from bit to bit, there's a factor of 2. And then you just add up where the 1 is, right? So this would just be 32 plus 8 plus 4 plus 1, which is 45, right? If I make a mistake, let me know. I think I added those correctly. All right, but this we already know, right? Because that's what we've been dealing with all quarters, just unsigned binary. Okay, but today we're going to talk about signed binary numbers, And there's actually three representations of sign binary numbers. There's sign magnitude. That's what that SM stands for over there. Sign magnitude. DRC, which stands for diminished. Okay, diminished radix complement. Okay, which is the same as one's complement, which you might have heard of in some other slides. And RC stands for radix complement. And radix complement is the same as two's complement. So you might have heard of one's complement, two's complement, in a different class. Now, out of these three, the most popular one is two's complement, okay, the radix complement. And that's our focus in this class. Okay, two's complement's the focus in this class. Also, CPE133, okay, the follow-on class of this one. When you deal with signed binary numbers in that class, you treat them as two's complement. Okay? But first thing, no matter what format you have, right? No matter which one of these three you have, when you have a signed binary number, the most significant bit, and remember, the most significant bit, that's the bit that's furthest to the left. The most significant bit is the sign bit. Okay? When you're dealing with signed binary numbers, the most significant bit doesn't have numerical value. It just tells you whether the binary number is positive or negative. And if that most significant bit is a 0, that means you have a positive binary number. And if it's a 1, binary number is negative. Okay? And again, that's true no matter what form you have, no matter which of these three you have, it's always true. The most significant bit furthest to the left, that tells you the sign. Now, if you have a positive signed binary number, so that means the most significant bit has to be a 0, and then the rest of the bits have value. So this is your sign bit. And when you find the value of a positive signed binary number, you do it the same way, no matter which one of these forms you have. So if I want to find the magnitude of this, whether it's sign magnitude, whether it's one's complement, whether it's two's complement, I find it the same way. Okay, there's no difference how you find the magnitude of a positive binary number based on these different types. What's different is how you find the value of a negative number. Because as you will see coming up, how you find the value of a negative number depends on which form you have, okay? But if it's positive like this one, the way you find the value is just like you would for an unsigned binary number, except this sign bit doesn't have value. But this would still be the ones column, right? The least significant bit. This would be the 2s, the 4s, the 8s, the 16s, the 32s, the 64s. Right, so you see in base 10, this would be positive. Let's see, we'd have to add up the columns that have a 1. So 64, 96, 96, 112, 116, 117, if I added up those right. Do you agree? Okay, let's go the other way. That's 5, 21, 53, 117. So I think that's right. Thumbs up. Anyone agree with me? Okay. And like I said, this would be true whether this was sign magnitude or one's complement, which is DRC, or two's complement, which is RC. In all three forms, if it's positive, you find the value the same way. Okay? All right, but like I said, what's different is when you have a negative. So let's say we have just want to make sure this agrees with my notes here. Let's say we have 1, 1, 1, 0, 1, 0, 1, and this is sign magnitudes. Okay, SM sign magnitude. Well, again, this most significant bit, that's the sign bit. That's what I mean by S. Okay, that's an S, not a 5. Okay, S for sign. Well, that tells us it's negative. And if it's sign magnitude, the way you find the magnitude of that negative number is the same way that you would for an unsigned or a positive sign number. But this is the ones column, this is the 2s, this is the 4s, this is the 8s, this is the 16s, this is the 32s. And then I just add up the values where I have a 1. So this would be 48, 52, 53 in base. Okay. All right, but now if I take that same bits, right? 1, 1, 1, 0, 1, 0, 1, and let's say it's ones complement, DRC. Okay, well, this is a ones complement number. Again, this is still the sign bit. That's always true. Most of the people, it's the sign bit. Well, again, that tells us it's minus. But the way you find the magnitude of a ones complement number is you flip the bits. So I would take these bits and I would flip them. Right? So I take these. Now I can flip the sign bit too, but what the sign bit is equal to originally, that gives you the sign. Now we're just trying to find the magnitude. All right. So really, to find the magnitude, it doesn't matter whether you flip the sign bit or not. Okay. But now, once the bits are flipped, now this is the 1s, 2s, 4s, 8s, 16s, 32. And you just add up where the 1s are. So we only have an 8 and a 2. So you see in a ones complement, this string of bits is equal to minus 10 in base 10. Where in sign magnitude, the same bits, right? The same bits in the same orders equal to minus 53. Because again, the way you find the magnitude is different when it's a negative sign binary number, depending on what form you have. Okay? All right, and then 2's complement, this is the most important one for this class. If we start out with the same sign binary number, right? 1, 1, 1, 0, 1, 0, 1, and it's 2's complement, okay, which is RC. Well, again, this is the sign bit, right? So that tells us it's negative. But to find the magnitude of a 2's complement, you flip the bits and then add 1. So I flip the bits just like I did for the 1's complement. And then I add 1. Right, so this is just going to be minus 11 in base 10. Right? Because it's just 1 more magnitude than what it was in 1's complement, right? Because I added 1 after I flipped the bits. Okay? So again, in summary, when you have a signed binary number, the most significant bit is the sign bit. It doesn't have numerical value. It just tells you whether you have a positive or negative number, right? 0 for positive, 1 for negative. When it's a positive sign binary number, the way you find the magnitude is the same no matter what form it is. Okay, but when it's a negative value, it depends which form, how you find the magnitude. And again, the one that's important in this class is this one right here. This is going to be the focus. There's a reason why 2's complement is more popular, in practical digital circuits. We'll get to the reason when we talk about the handout, which we're ready to talk about actually right now. Okay, look at the agenda. We're at the handout. So at the table or at your table, there should be 4 copies of the handout that shows 4-bit sign binary for each of the forms. Okay, the sign magnitude, 1's complement, and 2's complement. Yeah, it's this form right here. I put enough handouts on the table so everybody should have their own copy. So take a look at this handout, and you notice something peculiar about sign magnitude and 1's complement compared to 2's complement? Just looking at these numbers that you can represent with these forms with 4 bits. You see anything about the sign magnitude of one's complement that kind of looks weird? Yeah, both these forms, sign magnitude and one's complement, have 2 values for 0. They have a positive 0 and a negative 0. And you know, what is negative 0, right? We think of 0 as being positive, at least most people, I guess. But look at 2's complement. Does 2's complement have 2 values for 0? No, it's only got 1 value for plus 0. In fact, what value does 2's complement have that 1's complement and sign magnitude doesn't have? Negative 8. So instead of having 2 values for 0, 2's complement only has 1 value for 0, and you pick up an added value. Right? Because it has a representation of negative 8 that the other 2 forms don't. So you see, that's why 2's complement is more common or more useful in a practical sense, because you don't have to worry about 2 values of 0. For most applications, you don't want 2 values of 0. Now, there might be some application out there where you do, but most of the time you don't. And plus, you pick up an added value. Okay? All right, so that's why 2's complement, you know, not only in this class in CPE133, but also, you know, in practical circuits, usually that's the form that's used. Okay. All right. So the next thing we're going to do is look at what range you have for both unsigned and 2's complement, depending on the number of bits you have. So let's start with unsigned. Okay, let's say I have unsigned 4 bits. What's the range of values that I can represent with unsigned and 4 bits? I can go from what number to what number? 0 to 15, right? Right, because if all 4 bits are 0, that's a 0. And if all 4 bits are 1, that's a 15, right? Okay, how about unsigned 5 bits? What would be the range of unsigned 5 bits? Yeah, it'd still be 0, right? Because no matter how many zeros you have, it's still 0, right? So 5 0 still going to be 0, and it'd be 31. Right? Because if you have 5 1s, you'd be adding up 1, 2, 4, 8, and 16, so 31. Okay. So if I wanted to write a general expression for the range of unsigned based on the number of bits I had, I could do this. It's always going to be 0, the lowest, right? But my highest would be 2 to the n minus 1, where n equals the number of bits. Right, you agree with that? Because like right here, if you take 4 bits and you put 4, right, you get 2 to the 4, 16 minus 1, which is 15. Right, if you have 5 bits, 2 to the 5 is 32 minus 1, 31, and so on. So you see, so here's the general expression for the range of values if you have an unsigned binary number. Okay, so everybody agree with that? All right, how about 2's complement? Okay, so RC, 2's complement, remember, radix complement, 2's complement, the same thing. That's 4 bits. Okay, what's going to be the range of a 2's complement 4-bit number? Actually, that's the one on your handout. What's the most negative I can represent with 4 bits if it's 2's complement? Negative 8. And what's the most positive? Plus 7. Okay, again, that's what's on your handout. That's 4-bit 2's complement. Okay, how about if I had 5-bit 2's complement? Can you guess what the range would be, or do you know what the range would be? What was that? Not quite. Because remember, one of the bits is signed that doesn't have numerical value. So that's why with 4 bits, it's minus 18 to plus 7 instead of minus 16, right? Because the most significant bit is the sign bit, which doesn't have numerical value. So that's why we can't go to -16 with 4 bits. Oh, how about 5 bits though? Can we go to -16? Yeah, right, because the 5th bit is the sign, you got the 4 other ones, right? So it'd be -16 to what? Plus 15. Okay, and if it was 6 bits, it'd be -32 to +31, and so on. So if I were to write a general expression based on the number of bits I have for the range of a 2's complement number, the most negative would be -2 to the n minus 1, and the most positive would be 2 to the n minus 1 minus 1. Because again, if you just plug in some numbers here, say you have 4 bits and you plug in 4 for n, that would be -2 to the 3rd power, that's -8. Right? And if I plug in 4 to the top side, I'd have 2 to the 3, which is 8 minus 1, which is 7. So does everybody see how I got this general expression? See, the reason you subtract 1 from the total number of bits is because 1 bit's a signed bit, right? So that doesn't have numerical value. Okay, so these 2 general expressions are handy. Okay, but every time this one I can kind of, just memorize. It's not that hard, right? Because one value is 0. But I don't really try to memorize this general expression. What I do is I just kind of go through the process I just showed you. I go, okay, well, I know with 4 bits, I can go -18 to +7. I know with 5 bits, -16 to +15. And then I just kind of figure out, what the general expression is from those examples. Or if I do try to just write this down from memory, usually I'll do this as a check to make sure, because it's very easy to get something wrong if you just try to memorize it. Okay? All right, so any questions up to this point? Is everything going pretty well? All right. Okay, the next couple of things we're going to talk about are not really important for this class, but the reason I'm going to bring them up is because they are something that's important to know for CPE 233. I suppose depending on what your final project is, you could run across this, but for any of the labs we do, we're not going to run into this, but you will run into this in CPE 233, and that's padding with zeros and also sign extension. And you're going to see that both of these things you already know. It's just they give fancy, titles or fancy phrases. So, things you already know. Okay. So what's meant by padding with zeros is, let's say I have an unsigned binary number in, let's say it's 6 bits. Okay, it doesn't really matter how many bits it is, okay, to get across the point. I hope to get across coming up, but I had to pick some number of bits, so I picked 6. So let's say we just have a 6-bit unsigned binary number. And again, there's no importance in what the particular bits are. It could be anything. But you see, sometimes you'll have an unsigned binary number that's a certain number of bits, and you want to make it a larger number of bits without changing the value. Like, let's say for some reason, and when you take CP 233, you'll see a reason for this. But let's say for some reason, I want to take this 6-bit unsigned binary number and I want to make it 12 bits, but I don't want to change the value. I want to keep the value the same. So how would you do that? How would you take this unsigned 6-bit number, make it into a 12-bit number without changing its value?
Just add zeros on the left side.
Yeah, just add zeros to the left, right? Because I don't change anything, right? I would just put 6 more zeros. Right? You already knew that. Well, that's what's called padding with zeros. See, adding zeros in front of an unsigned binary number to make it a larger number of bits without changing its value, that's what's meant by padding with zeros. All right, so they just gave it a fancy phrase for something you already know. Okay? All right, well now, let's say we have 2's complement. Okay, so RC, 2's complement. So, we have signed binary numbers. And let's say, one of them is positive. Okay, so let's say it's those 6 bits. Again, the actual value doesn't really matter for what we're talking about here. But it's positive because the most significant bit, which is the signed bit, is 0. And let's say we have another 2's complement number that's negative of some value. Again, the value doesn't really matter for what we're talking about here. Okay, but we have 6-bit 2's complement numbers. One's positive, one. Okay, well, let's look at the positive one first. Let's say that I want to make this positive 2's complement number 12 bits, right? It's 6 bits, but I want to make it 12 bits, and I don't want to change the value. So what would you do? I want to make this 6-bit 2's complement number 12 bits without changing its value.
You have to check to see if the most is a 1 and if it's not.
Well, just looking at this one, we're not. I wrote this down, but let's not look at this one yet. Let's just look at this one. But you're seeing where I'm going. But let's go with it. So, yeah, you would do the same thing as you would with an unsigned binary number, right? You would just add 6 zeros to the front. Right? Because again, that's not going to change the number based on how we find the value of a 2's complement positive number, which is the same as what we do for an unsigned, right? Okay, but now, and Gus, right? You mean Gus. I think this is what Gus was looking at. Now, let's say we have a negative 2's complement 6-bit number like this. And again, I want to make this 12 bits, but I don't want to change its value. So what would you do here? Because remember, how do you find the magnitude of a 2's complement negative number? What did we do over here? You flip the bits, then add 1, right? So if I don't want to change the value of this and make it 12 bits, what am I going to add? 1's where? Yeah, in the front. Right? I would just add 6 1's. Right? Because when I flip the bits and add 1, I'll get the same value as I did when it was 6 bits. So if it's a 2's complement number and you want to make it a larger number of bits, you do what we call sign extension. You just take the sign bit and use the sign bit for the extra bits. Right? So you see, this is called sign extension. Okay. See, if I had put zeros in front of this negative 2's complement, well, when I go to flip the bits to get the value, those zeros are going to turn to 1s. And those 1s in front of all these bits, that's going to change the value, right? See, that's why I don't put zeros in front of a negative 2's complement if I want to make it a larger number of bits without changing the value. Okay? So that's what padding with zeros and sign extension is all about. Okay. So any questions? You guys have a question or no? Okay, so the next thing, if there's no questions up to this point, the next thing we're going to look at is addition with sign, binary number, and again, we're focusing on 2's complement. So we're going to look at adding 2's complement numbers and also doing binary subtraction by addition with 2's complement numbers. Okay, so you ready for that? Okay. Well, also, I just want to make sure no questions up to this point, because I'm going to erase what I have up here to make more room. Okay. All right, I'll erase this. This will give us enough room. So I'm going to show you sign binary addition and also sign binary subtraction by addition with some examples. Now, before we get to the examples, anytime you're doing sign binary addition or sign binary subtraction by addition, you always want to make sure that your result is valid. Okay, you always have to do what we call a validity check on any answers from the addition or subtraction. So here are the rules of validity. If you take a positive two's complement number and add it to a negative two's complement number, it's always valid. You can prove it on a number line. But when we do some examples, I'll show you another way that you can prove it. Okay, if you take a positive plus a positive, valid if result is positive. Right? It doesn't make sense to take two positive. Again, if you think of a number line, it doesn't make sense, right, to take two positive numbers and get a negative answer. Right? So two positives is going to give you a positive. Okay, and if you add two negatives, well, valid if result is negative. All right, so these are the validity rules.
Positive numbers, negative numbers.
Yeah, you're going to see. And there's another way to look at this that I'll also talk about. Okay, so yeah. Yeah, if after I do these examples, you still have a question asked. But I think when we do the examples, it will answer your question. Okay. All right, so let's go through these examples. So we'll start with this one right here. Now again, because these are signed numbers, the most significant bit, that's a sign bit. Okay, so that's our sign bit right there. So you should be able to tell me, based on these rules, you should be able to tell me, is the result of these two being added, these two signs, two's complement numbers, is it going to be valid or invalid? Yeah, valid. Why? Yeah, we're adding a positive to a negative, and again, positive plus a negative is always valid. So this result is going to be valid. Okay. All right. So now, when you add these manually, when you add these signed binary numbers manually, you add them the same way as we were adding unsigned, right? You go column by column, starting with the least significant bit column. So 1 plus 1, 0 with a carry of 1, 1 plus 1 plus 1, 1 with a carry of 1, 1 plus 0 plus 0, 1, 0 plus 1, 1. Now, just like these are the sign bits of what we're adding, this here is the sign bit of our results, right? Because again, for this to the left, your most significant bit, that's your sign bit. Now, we could also, just to double check that, this is a valid addition, we can take these two's complement numbers and convert them to base 10. Because what is this in base 10? What is 0011 in base 10? It's positive what? What is it? 3, right? Because 1, 2. So this is plus 3 in base 10. What's 1011? Two's complement in base 10. Remember, this doesn't have numerical value. This is the sign bit. So that tells us it's negative. And since it's negative, what do you have to do to get the magnitude of it? You got to flip it, and what else? Add 1. So you see, if I take this and flip it, I'm going to get 0, 1, 0, 0, right? That's flipping this. And then I add 1, 0, 1, 0, 1, that's 5. Right? So you see 1, 0, 1, 1 in two's complement is minus 5 in base 10. So I'm adding plus 3 to minus 5. Obviously, I should get minus 2. Do you agree that this is minus 2 in two's complement? Right? Because see the result, the sign bit is 1, which means it's negative. And now if I take 1, 1, 1, 0 and flip it, I get 0, 0, 0, 1, and then add 1, 0, 0, 1, 0. See, that's minus 2 in base 10. Okay? So does everybody see what we're doing here? Because if you see this one, it's basically just more practice. Now, there's a few unique things that are going to come up that I'm going to point out. But if you understand this one, it's sort of more the same coming up. Okay, all right, let's do the next one. Again, this is the sign bit. So I go ahead and I add the columns just like they were unsigned, right? So 1 plus 1, 0, carry the 1. 1 plus 0 plus 0, 1. 0 plus 1, 0, 0 plus 0, 0. So is this valid or invalid? Based on our rules. Did you give me a thumbs up? You're right. Why is it valid?
Because they were both negatives.
Or both what? Yeah, both positive. Yeah, exactly. We're adding two positives and we're getting a positive result. So it's valid. And then again, if you want to just double check, you can just convert these 2's complement to base 10. What is this in base 10? 1, right? Correct 1. What's this in base 10? Plus 5. And what's this? Yeah, plus 6. Okay. All right, ready for the next one? This is the sign bit. 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. Okay, is it valid or not? Valid or invalid? Why? Yeah, we're adding a negative and a positive, which is always valid. Okay, let's double check with base 10. 1, 0, 0, 0. What's that in base 10? What's this 2's complement number in base 10? Negative what? We don't have a negative 0 in 2's complement, remember. Yeah, again, that's the big advantage of 2's complement over the other forms is you don't have a negative 0 with 2's complement. So what is this one? It's on the handout. Yeah, it's -8. See, it's -8 because the 1 for the sign bit tells us it's negative. And now to get the magnitude, I flip these bits. So it'd be 0, 1, 1, 1, and then I add 1. Which gives me 1, 0, 0, 0. Okay, so this is -8. Okay, how about this one? What's this? That's plus 4. So is this -4? Yeah, because sign bit to 1 tells me it's negative. And then to get the magnitude, I flip these. Right, so 0, 1, 1, and I add 1, that gives me 4. Yeah. So everybody agree on this one? All right, let's do the next one here. Okay, the next one, 1 plus 1, 0, carry the 1, 1 plus 1 plus 1, 1, carry the 1, 1 plus 0 plus 1, 0, carry the 1. Okay, remember again, this is the sign bit. Valid or invalid? Invalid. Yeah, why is it invalid?
The results. It's negative.
Yeah, we're adding two positives and we get a negative result, right? That doesn't make sense. This is invalid. Now, what is this number in base 10? 3. That's a plus 3. What is this number in base 10? Plus 7. Plus 3 plus 7, as you know, is 10, right? Plus 10. Can I represent plus 10 if I have 4 bits for my 2's complement? No, what's the most positive number I can represent with 4 bits if it's 2's complement? 7 plus 7. So you see, that's another way to determine if you have an invalid addition, is that if your result is outside the range that you can represent with that number of bits, well, it's going to be invalid. See, 1, 0, 1, 0, if this wasn't the sign bit, right? 1, 0, 1, 0 is 10 is binary for 10, right? But you see, this doesn't have numerical value. This is a sign bit. See, that's what makes it impossible for 2's complement with 4 bits to represent a plus 10, right? Because this sign bit doesn't have numerical value. Okay. All right, let's do another one here. Let's do this one. Again, that's the sign bit column, okay, but we just add on like they're adding multi-bit binary here. So 1 plus 1, 0, carry the 1, 1 plus 1 plus 0, 0, carry the 1, 1 plus 1 plus 1, 1, carry the 1, 1 plus 1 plus 1, 1, carry the 1. So I chose this example because something occurs here we haven't seen before. Look what happens when we add these, we get a 1 to the left of the sign bit. Right, we're getting this 1 to the left of the sign bit. What do you think we do with that 1 to the left of the sign bit? What do you think we do? What if you had a base 10 number where there was some digit to the left of the sign? What would you say about that? Does that make any sense? No, it doesn't make any sense. You would just ignore it, right? Same thing here. You just ignore any bit to the left of the sign bit. It just doesn't make sense. Okay? All right, so is this valid or invalid? Valid, right? Because we're adding 2 negatives and we get a negative. So it's valid. Again, we can check it in base 10. What's 1, 1, 1, 1? 2's complement. What's this in base 10?
Negative 1.
Yeah. Right? This tells us it's negative. Then to get the value, I flip all the bits, add 1. So it's going to be negative 1. What's this? In base 10. Negative 3. Negative 3. So I should get negative 4. Is this negative 4? Yeah, because I flipped the bits, 0, 0, 1, 1, add a 1, gives me 4. So negative 4. Okay? Okay, one more before we get to subtraction. Okay, so 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 0 is 1. 1 plus 1 is 0 with a carry of 1. Okay, so again, we get this bit that's to the left of the sign bit, so we just ignore it. So what would you say about this? Not invalid, right? Because we're adding 2 negatives and we get a positive, which can't happen. So this is invalid. Okay, and if you look at the range here, because what would this number be in base 10? 4. Minus 4. How about this one? Not minus 1. Remember, you got to flip the bits and add 1. Yeah, so minus 7. So look, we're adding minus 4 and minus 7, which is minus 11. Can you represent minus 11 with 4 bits in 2's complement? What's the most negative number you can represent with 4 bits in 2's complement? Negative 8. So again, invalid because it's outside the range. That's another way to look at it. Okay? All right, so any questions about how you do signed binary addition and how you determine whether it's valid or not? Okay, well, if you understood signed binary addition, binary subtraction by addition, basically the same thing except for one important step. But before we see some examples, you may wonder, why not do just straight binary subtraction? And you could, because remember a few weeks ago when we first started talking about adding bits, right? And I had those rules like 0 plus 0 is 0, 0 plus 1 is 1, and so on, right? Those were our rules of single bit addition, and that led us to a couple of truth tables, and we even did some Carnot maps, and we came up with the adding circuits from those rules, right? The half adder and the full adder. Well, there are subtraction rules too. To tell you the truth, I don't remember what they are. I mean, I'd have to Google them. I think the last time I saw subtraction rules for binary was when I was taking a class like this a long, long time ago. because you never see, or at least I've never seen, and it's not readily seen, I guess I can say. I'm sure someone's seen it, but I haven't seen a logic circuit that does straight subtraction. Okay, all I've ever seen is logic circuits that do subtraction by addition. And why would that be an advantage? Like, why, if you had the choice of doing subtraction by addition in binary as opposed to doing straight subtraction, why do you think that would be an advantage?
You just only have one addition circuit.
Exactly. It's the same hardware, right? That the same hardware that you designed to do addition, that ripple carry adder, can be used to also do subtraction by addition, right? If you did straight subtraction, like you took the rules of subtraction and put it into a truth table or a K-map, you would see you come up with a different logic circuit. You'd have different hardware. Okay, so you're reusing hardware you already have by doing subtraction by addition. Okay, so that's the big advantage. So as you're aware, if you want to take some number minus another number, well, that's the same as taking this number and adding it to the negative of this number. Okay, and in 2's complement, there's actually like two meanings depending on whether you take 2's complement as a noun or 2's complement as a verb, like an action. See, 2's complement as a noun, I have it written up here. That's like on the handout, right? Where you just have a listing of the 2's complement numbers for, 4 bits on your handout. And, you could have another listing of 5 bits and so on. So that's 2's complement as a noun, that listing of a binary that represents the signed binary numbers. There's also 2's complement, the verb. We'll say that we take the 2's complement of a number, and it can be a negative number, it can be a positive number. I can take the 2's complement of any number. And when you take the 2's complement of a number, you get the negative. It negates it. So as an example, we're going to go through and do these 3 problems here, where this is A, and this is B. It's A, and this is A. So I'm just going to copy down A, because we don't do anything to A. We only negate B. So I'm just going to copy down A. Okay, and now we're going to add it to the negation of this. And to get the negation, we take the 2's complement. So I'm going to take the 0, 0, 1, 1, flip the bits, and then add 1. Right? So you see, I'm just taking this, taking the 2's complement, right? Flipping the bits, adding 1. So 1, 1, 0, 1. Now, if you want to prove that we have negated this, well, what is this? And remember, these are the sign bits here, the most significant bits. Okay, what is this in base 10? What is 0, 0, 1, 1 in base 10? Treating this as a 2's complement, where this is the sign bit. What is it? It's plus what? Plus 3, right? Remember, if it's positive, then you just treat this like an unsigned, right? 0, 1, 1, I got a 1, I got a 2, so 3. All right, well, look, after I take the 2's complement of that plus 3, what's the value of this? The sign bit's 1 now, so it's minus. Isn't this minus 3? Right? Because since it's now a sign bit of 1 means it's negative, and to get the magnitude, I flip the bits, right? So 0, 1, 0, then I add 1, which is going to give me 3. So you see, I took the 2's complement of this plus 3, and it made it minus 3. It negated it. Okay? And now I just add those two. Right? I just add them like, see, once you've done this, once you've negated the second number, now it's just this again. It's the same as we're just doing addition. So it's 1 plus 1, 0, carry the 1, get a 1 there, 1 plus 1, 0, carry the 1, 0, 1. Did I do that right? 1 plus 1, 0, carry the 1. 0. And again, we would ignore this bit here because it's left with a sign bit. So you see we're taking plus 5 and we're adding it to minus 3. Is this a valid result? Yeah, we're adding a positive and a negative, so it's valid. And then if you check it with base 10, this comes out to plus 2, right? This is 2 plus 2. Okay, so when you're doing binary subtraction by addition, really the only thing new is taking the 2's complement of that second number, because that's what negates it. Then it's just doing addition like we did over there. It's just a repeat of what we were doing previously. Right? All right, let's do another example. Let's do this one here. So again, you just take A the way it is, the 1, 0, 0, 1. And then we're going to add it to the 2's complement of this. We're going to take the 2's complement of this. So if I take the 2's complement of this, what am I going to get? 0, 0, 1. 0, 0, 1, 0. Yep. Okay, everybody see how we got that right? We flip the bits, 0, 0, 0, 1, then we add 1, which makes this 1, 0. Okay. And again, if you want to prove that it actually negated it, okay, this is minus what? I remember you got to flip the bits and add 1, right? Remember, it's a 2's complement and it's negative. To get the value, we got to flip the bits and add 1. So if you flip the bits and add 1, what's this? It'd be 0, 0, 0, 1, add 1. It's minus 2, isn't it? Right? You see, we take the 2's complement and we get plus 2. Okay. All right, and then you just go ahead and add them. So 1, 0, 0, 0, 1, 0. This is the sign bit. So let's see, yeah, 1, 1, 0, 1. And can you tell me if this is valid or invalid? Valid because we're adding a negative to a positive, so it's got to be valid. It's like this one was valid. And what? This is minus what? 7 and 7. And we're adding that to plus 2, right? And is this minus 5? It is. Okay, one more. All right, so again, we just copy down A the way it is. Then we're going to add it to the 2's complement of this. So I take the 2's complement of this, what am I going to get? Zero, 1, 1, 1. Right, because it'll be 0, 1, 1, 0, add 1, and pick up this 1 right here. So again, if you want to prove that it actually negated it, this is minus 7, right, in base 10, and this is plus 7. Okay, and then we go ahead and add, so 0, 1, 0, 0, plus 0, 1, 1, 1. Get 1, 1, 0, carry the 1. So what would you say here? Invalid, right? Because we're adding 2 positives, it comes out negative, so this is invalid. Because you can see it's 4 minus a minus 7, right? Which is 11 plus 11, which again is outside the range. Okay? Okay. Oh, I forgot to turn the camera. Boy, I ruined my streak. I had about, counting my other sections, I had to have had, I was almost approaching double digits. I didn't quite make double digits. I blew it just like my Bruins blew the hockey game the other night. So I got Bruin jinx in this. All right. So anyway, Any questions about anything up to this point? What's left before you can start doing the activities? I just want to show you the activity on Canvas on the projector. Also, just talk a little bit about Lab 4, because like I said, there's a small part of Lab 4 that you can do today after the activity. And then I want to talk about some things that came up during Lab 3 that kind of pertain to the rest of the quarter as far as troubleshooting. So probably another 10 minutes. Okay, that shouldn't be too much longer. So let's look at the activity on Canvas. So we don't have any hockey fans out there. Duck fans or Shark fans or what other California teams are there? Those are the only California hockey teams, right? The Ducks and the Sharks. Oh, Kings. The Kings are good. They're in the playoffs, aren't they? Or they lost to Lakers and Warriors. I don't like the Lakers. I don't like the Warriors either, so I don't care who wins that series. As long as they lose to whoever they play next. I'm a Boston fan, so but I'm more of a Bruins fan than a Celtics fan. I like the Celtics, but I like ice hockey. Okay, but anyway, here is the activity. Now, there's actually two activities. There's a worksheet, and here's the answers to the worksheet. And then there's also another activity. This worksheet is mainly just on the different forms and like ranges that you can get depending on how many bits you have. And then this other PDF, those have addition and subtraction problems. Okay, and if you take a look at the addition and subtraction, you'll notice that there's two problems numbered the same 10, but they're different. And I just want you to do the problems that are circled. So there's like 7 here, and another 6. So there's a total of 13. If you look at the other worksheet or the other worksheet, you know, it's more like, you know, talking about the numbers. Now there is one mistake. Number 6, this should be what is minus 27. Not plus 27. If you look at it, okay, so that's the activity. The lab. Okay, here's lab 4. And like I mentioned, there's quite a few modules. Now, most of these modules you've seen, right? You see there's 3 muxes. There's a couple of ripple carry-adders. This is your decoder from lab 3, your 7-seg decoder. Now, you have a new module, a validity checker. I'm going to talk about the validity checker on Thursday. But what you can do after you finish the activity, what you can do today is, one, you can create a new project for your lab 4, because remember, for each lab, you should have, you know, its own project. And then notice, these RCAs, these ripple carry-adders, they're a little bit different than what you presently have for an RCA. Do you see what's different? It's on the input side. Yeah, right now, you only have A and B inputs. You don't have a C input into your ripple carry-adder. So one of the things you can do before Thursday is take your current RCA, okay, the one you already have, like you can copy it over to your new project for lab 4. And your RCA right now has 3 full adders and a half adder, right? Okay, that's what your RCA has right now. Well, before Thursday, what you could do is modify the RCA you already have. Like, don't start from scratch. Take what you already have and modify it so it's made out of all full adders. And then the carry in of this least significant full adder, the one that replaces the half adder, that connects to the carry in of the RCA. Right? So you see this carry in right here of the RCA would just directly connect to the carry in of the full adder that replaces the half adder. Now, there's a reason we're doing this. And I'll explain the reason on Thursday. It actually makes, by doing this, we're saving some hardware. If we didn't do this, we could do something else, but it would require more hardware. Okay, so, and then I got some emails over the weekend. I don't remember what, I think it was basically people from all my sections, a couple people from probably the section. But it had to do with troubleshooting, and this general troubleshooting document is on Canvas. If you go on Canvas, I don't know if you've looked at all of it. Sometimes just from the questions I get, I don't think people are looking, or maybe they looked a long time ago and they didn't really know what they were looking at because we hadn't talked much about anything, but at the beginning. But if you go to Canvas, there's a whole part of Canvas that's lab resources. So you might want to look there, just to see what's available. And one of the things is this document that has like general troubleshooting steps. Because over the weekend, I got some questions where, I have a suspicion, I don't know for sure, but I have suspicions that people are not going in order, okay? For example, you should never download to the board to test your design until you have simulated all your lower level modules and your overall module. Okay, I have a feeling there was some people that are just downloading and seeing if it works, and they're like, oh, it doesn't work. Well, you got to simulate it first, right? Because if it doesn't simulate correctly, it's not going to work on the board. Okay, and also you simulate your lower level modules first, and then once those are working the way you want them to work, then you do the overall. Because if your lower level module or modules are not working, the higher level is not going to work. Okay. Okay, the other thing is, and again, I know I've said this before, and I'm repeating myself, but again, it's important that you work with your lab partner, right? Like I said at the beginning of the quarter, the main reason I like to have two people in a group where each person is working independently is that if one of the people run into a problem, you have somebody like as a soundboard, if you will, to go to and say, hey, I run into this problem. Did you run into this problem? Chances are they're not going to run into the same problem if they're doing their work independently. And then you can learn from that person, right? You can learn from each other. I think about when I was a student, I learned more from my peers than from my instructors, right? Just working things out with, people in the class. And now, back then we didn't have as many resources as you have now. Of course, there's no internet and all that kind of stuff. Like I can remember, most of the textbooks back then, they would have answers to like the odd numbered homework problems in the book, but the instructors would always assign the even numbers, right? So you never knew. So, but it was good. When I look back on it, it was actually good from a learning point of view, because we would actually get together before turning in the homework and we'd compare answers. We'd be like, oh, what'd you get? And you like have to defend your answer, if you had different answers. And it was very, looking back, again, I didn't know it at the time. I just thought it was a hassle at the time. But looking back on it, it's where I learned the most, actually. So anyway, that's what I'm kind of looking for, is that, you work independently, from your lab partner, but also you work together when someone's having a problem, because both people learn that way. Not just the person that ran into the problem, but the person, that helps. Okay, but getting back to this, so, make sure you simulate lower level, then the overall. Now, if you have trouble with the simulation, like you're not getting the right simulation, the problem can either be in the design source or the simulation file, or both. It could be either of those or both. Also, this came up this weekend. You know, if your timing diagrams in your simulation, right, you do the simulation, you look at the timing diagram, and if all your waveforms are green, I mean, that's good. At least they're not blue or red, because if they're blue or red, something's not right. Because when a waveform in your simulation timing diagram is blue or red, that usually means something's not declared right, or you're missing something. Like the most common thing that came up in lab 3 from the people that contacted me is, you know, in the diagram where you're connecting the sum output of the RCA to the input of the decoder, and they're both 4 bits, and they're lower level, so you have to make an internal signal in order to add them. Well, that internal signal has to be the same number of bits as the bits you're connecting. And a common mistake is, you know, they only have the internal signal as 1 bit instead of 4 bits. And they were seeing, you know, people that caught that in the timing diagram were looking and they're like, oh, it's only reading 0 or 1. That's because it only had 1 bit, right? You can only read 0 or 1 if there's 1 bit, okay? But the main point I want to make is, if your timing diagram, if the waveforms are all green, I mean, that's better than having red or blue, but it doesn't necessarily mean that the simulation's working. You actually have to look at those green waveforms and make sure you're getting the right truth table. I think there were some people, they just looked and yeah, the waveforms were green. They thought, oh, everything's fine. But then when they downloaded it to the board, they saw it wasn't working right because, yeah, it wasn't following the truth table. Okay. Now, the other thing here is, if you have a good simulation and then you get an error after that, like you get an error while you're implementing or generating the bit stream, chances are the problem is with constraints. Okay. Again, I think I mentioned this before, but it's important enough to say again. What the constraints is doing is taking your logical names of your inputs and outputs and associating those names with physical components on the basis board, right? It's taking whatever you called an input and assigning it to a switch, or whatever you call the named it output and assigning it to an LED or a 7-segment display or whatever it may be. You don't even need the constraints file to do a simulation. Right? The constraints file has nothing to do with the simulation. But if you got a good sim and it's failing after that, chances are it's constraints. And one thing to always keep an eye on when you modify your constraints is be careful with the parentheses. You know, when you look at the constraints file, there's like 3 different parentheses. There's the normal parentheses, there's the brackets, and then there's the braces. And if any of those are incorrect or missing, you're going to get an error at the very least. I've had students where their computers have crashed because they were like missing a brace or something, or they had a brace where a square bracket should go, or something like that. So just be really careful with those brackets and braces and parentheses in the constraints file. But there is one exception to look out for, and that's if your simulation is good and when you do the implementation or generate the bit stream, if you get a message where it's something to the effect of failed due to earlier errors, where you didn't have an earlier error, what it really means, because it's kind of like Bavado is mocking you, you know, because they're saying failed due to earlier. Well, I didn't have an earlier. But really what it is that there was a warning that you probably got that really should have been an error. Okay, and it's that warning that's giving you a problem. Okay, and then the only other thing I'll say, and I'll let you go. I know I've been talking a lot. But the last thing is, if you ever get an error message or a warning, mainly error messages, where it directs you to a log file, like it will give you a path name and it ends with the log file, look at that log file, because even though the messages a lot of time are very cryptic and not very useful because you're looking at it and you're like, what does that mean? But usually in the log file, they have more descriptive of what the problem may be. I've always found the log file more useful than any of the messages that are given. Okay? All right, so if you don't have any questions, are there any questions before you get started with the activities? And like I said, once you're done with the activity, you can do a little bit of lab 4, but I'm going to spend probably 40 minutes at the beginning of Thursday's class talking about that diagram, that lab 4 diagram, like what's going on. And then after that, you'll be able to accomplish lab 4. And like I said, lab 4 is not due until Friday of next week after the midterm. Okay? All right. Well, if questions come up, please ask. And Ethan won't be here today. He had a family emergency that came up. He'll be back next week. But I will